This week we're going to talk about relativity because we never covered it, and half of this lecture, you're going to be like, "Yeah, I get it. Okay, yeah, right." But it is important that I teach you this because I was thinking like, "Oh, we're going to go on to, inelastic and elastic collisions now that we have the energy down." But I was like, "No, I can't do that because I haven't taught you relativity yet." So there's three types of relativity. There's Galilean relativity, there's special relativity, and there's general relativity. This one's very famous. These were both created by Einstein. I think this one don't quote me on this, but it's about 1905, maybe like 1917. It's around those times, right? Galileo, his relativity was like in the 1600s. I don't know exactly when, but that century. Okay? You can look it up if you care. So Galilean relativity, Galileo had a principle, right? It's Galilean invariance. By the way, is there any way to get me to... That is Dr. Bottom. Can I just get it to go away? Usually it just hides itself. Okay, well, we'll just stick it at the top, whatever. So... That really annoys me. Okay, whatever. Galilean invariance. And what this says is that the laws of motion, right, are true in all frames of reference if they're true in one. Okay, anything that's true in one frame, if there's a law of motion, is true in all frames, right? If you look at in video games, right, you have a point, and you have your world space, and you have your local space. Okay, then whatever's true in the world frame is also true in the local frame. We don't have to do a specific set of new physics for the local frame. Physics is just physics, right? You do it in the world frame, it will carry on to the local frame. Now, having said that, okay. In inertial frames, alright, okay, or inertial frames of reference, right? And what that means is that they aren't accelerating. Because if you have a particle system, right, you can set it to be local or world frame. But if you start accelerating it, then suddenly the particles aren't going to be in the right place anymore, right? So we'll talk about that in a moment. You've also got, rotations can be applied. You can actually mess up rotations. I might do you a lesson on Quaternions at some point, but if you look at this is a cube, and you might not instantly recognize it's a cube because I made the cube a child of another cube, and this one looks like this one looks like this, and if I make them children of each other, well, it's fine if I've already done it. Oh, why is this stupid thing? I can't move my mouse because of the... it keeps darting everywhere because of my tablet. There we go. See, it looks fine there, but if we... Essentially, if we make a cube, give it a random rotation, right, and then give it a random non-uniform scale, right, and then we make a child of that object, and we start rotating this, right, and giving this, right, once you start rotating it after it's been given an, you see that the cube collider is now in the wrong place, and the whole thing's distorted and messed up because of how the matrices work. And then as soon as I drag it off there, it becomes normal again, right? So you've got to be careful about that. But you know, maybe if I'm feeling brave, I'll give you a lecture on Quaternions, which are extremely complicated. But it's just a result of how matrices work. This might actually stretch out into 2 lectures, this one, because I've written my lecture notes and I realised like I got I got really far and we're probably not going to be able to cover it all. But it's not 2 lectures worth, it's maybe like a lecture and a bit. So, anyway, Galileo, why did any of this exist? Well, he was a heliocentrist, right? He believed that the Earth moves around the sun, right? There's heliocentricity. And other people disagreed. And if you look, if you're on the Earth, you might think, okay, well, the stuff's moving around me, the sun's moving around me, I can see the stars, they appear to be moving around me. Now, of course, the North, you know, Polaris doesn't move much, whereas the ones at the equator will move a lot. And that's because, as we know now, the Earth is spinning on an axis, so this bit barely spins, right? Whereas this bit, relative to us, spins a lot. Okay? And now it's looking like a certain other planet that's not Earth. So we're going to talk about... So the proponents of this argument were like, well, I don't feel like the Earth's spinning. If the Earth was spinning, I'd know, right? Like, if the Earth was moving so fast, why wouldn't I feel it? I mean, Ptolemy was like, well, if the Earth's rotating, then why isn't there such winds hitting us all the time? Okay? And Galileo was like, okay, he thought about it and he came up with a thought experiment. He's like, what if there's a boat, and in a boat there's a little pirate, yar, well, not pirate because they haven't been invented yet, but maybe just like a sailor. And underneath the hold, there's a fish in a tank. You can't see anything because it's like, you know, the old days. They weren't like mounting glass windows. It's not like a submarine. You're below deck. You can't see anything, and there's like balls. He could have a ball, right, and bounce it off the walls. And as long as the boat is moving smoothly through the water, there is absolutely no way for this guy to know whether he's docked or at sea. Okay, he might be able to hear the waves or hear the motion, and obviously no motion is completely smooth. But in general, right, it's difficult for him to tell whether he's even moving as long as he's moving at a constant speed. Or moreover, if you're in the bird's nest of the ship, that's what we call this, right? And it's more like a cowboy than a pirate, though, isn't it? Oh well. There's a cowboy in the bird's nest, and he drops his revolver, right? Then, I'm sure this is not the example that Galileo used. Then he'd realise that this, right, even if the ship's moving very fast, the gun doesn't go this way, right? It just falls straight down. Well, okay, it goes a little bit, because as we know, there's drag. But there's not much drag on this because it's quite massive. If he drops a sword, let's say he is actually a pirate, and I can draw pirate hats, I can't, and he drops his sword, right, then the sword's going to just fall straight down and it's going to hit the deck. It's not going to go backwards. So he was like, well, there you have it. Now, this isn't actually a correct argument. It is a correct argument for inertial frames, right? So frames that are not accelerating, right? But the Earth is accelerating because the Earth's moving, you know, you move at a constant speed, right? The speed of the Earth around the sun isn't changing, but the direction's changing. And velocity depends on direction, so therefore there must be an acceleration, and that acceleration's due to gravity, right? That's what's moving you round. And the Earth, when the Earth rotates, you know, you're something on the surface is actually this experiencing acceleration all the time around the Earth. And because of that, it is possible to tell that the Earth's rotating. It's possible to tell that you're in an accelerating frame. You need a Foucault's. Is that even how it's pronounced? Pendulum. I should really know because I've done this experiment. But it's basically a really hypersensitive pendulum, right? And it can detect all these imaginary forces you get, like the Coriolis force. And some people might even tell you that if you're in the southern hemisphere, the toilet water flushes around the other way, right? That's not true. It's not true. Right? The reason the toilet flushes different ways is just because of the jets, right? The Coriolis force is not enough to make the water go the other way. I'm sorry that to if anyone heard that before and to spoil the illusion, but it is in principle correct that things spin differently on the southern hemisphere than they do on the northern hemisphere, and we'll get into that later. But we haven't even covered rotation yet, so that's a job for another day. But the job for today is that I am on a train. Okay, I can't draw trains. I can't even draw, to be honest, but we still make do. So this is a train. My name's Alex, and there's Brenda is looking at me, right? And I have blacked out windows on my train, so I can't tell that I'm moving. Now, there's this Galilean relativity is otherwise known as common sense, in that we all know this. We all learn it as small children before we can even talk. We all figure out this. And it's so natural to us that we don't even think about how complicated it is, that there are different universes for everyone, and we're just like, oh yeah, and it all just makes sense, right? So, wait, what is this more? Okay, right. So, oh, that's why I had chat messages, right? So, this is the train. I decide to throw a ball at the back window of the train. Okay? And out of this, relative to me, I threw it at 10 meters a second. Brenda sees the train moving forward, and she sees the ball moving forward. In her eyes, the ball goes like this, right? And the train goes like this. Now, in my eyes, the ball goes like this. Well, it doesn't just go horizontally and stop. It goes like that, right? So we disagree about what happened with the ball. We know how to agree because we instinctively understand how relativity works. So we can agree. But in general, let's say we have a van, right? Or a bumper car by the looks of it. And then I'm standing on top, and I throw a ball right up. As far as I'm concerned, the ball comes up, the ball comes down, assuming no air resistance, right? But in Brenda's frame, right, it goes like this. Okay, it goes in a parabola. As far as I'm concerned, there is no parabola. So the stuff we agree on, right? We agree on the laws of motion. We agree that gravity accelerated this ball. And we agree on the gravity strength. If we measure it, we see the gravity strength as the same if we were, trying to somehow record it. We agree that Newton's third law occurred. If it was a heavy ball, you'd see me go, ooh. Or if I fired a rocket launcher up, right, you'd see the recoil. Okay? We agree on Newton's second law. We agree how much force was transferred to it. We agree on conservation of momentum. We agree on, although to be honest, here I'm adding energy into the system by throwing it. But if I threw two balls and they bounce off each other in midair, we'd agree on how the momentum is conserved. We agree on the conservation of energy. We even agree on the time that it was in the air. and we agree on the height it went to, right? But what we disagree on is the x position, right? We disagree on the velocity, and we disagree on the depth, right? Because I'm like, well, it was 100 meters away from me, and you're like, no, it was 0 meters away. So there's things we disagree on. Okay, we also kind of disagree on the initial height as well, because you're like 1 meter off the ground, right? But we agree on the difference in height. We agree on the dy. We just disagree on the y. We agree on the dz as well, right? But we disagree on the dx, right? So there's things we disagree on and there's things we agree on. So what we have here is this thing called a Galilean transformation. And I'm going to make it sound more complicated than it is because you already know it intuitively. But when we write it down mathematically, it somehow looks harder than it intuitively is. Right? So we have x, y, and z. And we have a moving frame. So maybe this frame is the world space, you know? And this frame is camera space or something like that, like a camera's moving. Right? And what we do in physics, we call this y prime, z prime, and x prime. Right? This is just the prime frame. Right? And this can be called all kinds of things. This one could be like the lab frame. But everything is a frame. There's no absolute frame to the universe. Right? So how do we get, if this prime frame is moving at v, right, but only in the x direction, then we can see that y prime is just the same as y. Z prime is just the same as z. But the transformation, right, to get something into the x prime frame is x prime equals x minus vt. Right? And you might be like, well, why minus? Because this, if you think about it like that, you know, this is my position here plus some velocity, so why isn't it plus? Why is this minus? Right, we'll look at an example. Alex in the train, or Axel in the train, right? And Bob's at the train station. And Axel is going to his Guns N' Roses concert, right? And he's trying to get there, and I'm trying to get there. Oh, no, I'm not trying to. Well, okay, it's me, right? It's me. I'm trying to get there, and it's not a Guns N' Roses conference. It's GDC, right? Right. So I'm trying to get to GDC on the BART. I've arrived in San Francisco, and I'm on the BART. One day you might know what this is, and Bob misses BART. It's actually BART, not the BART, but whatever. Bob misses BART. It's a metro. It's a metro link. It's like the London Underground. Bob misses the train, right? Now, Bob looks at this and says, well, the distance is d, and I'm waiting for a new train, and the distance to the conference is d. I say, well, no, the difference to the conference isn't d. We've got speed as distance over time, right? And I'm getting closer and closer. And because I'm not accelerating, the train just happens to be. I jump on while it's moving, and the train doesn't accelerate at all. So once we're halfway through, right, this gap has got smaller. So it started at d. So much like y equals mx plus c, we started with this, the x distance, right? This x is equal to some constant, so d, the initial distance, minus vt, right? We're subtracting the sort of this distance. The speed is the distance over time, so we can multiply the time by the speed, and we can see that this decreases. So for me, x equals d minus vt, right? For you, xb, okay, that's xa, xb equals d. So we can say that xa equals xb minus vt, or x prime equals x minus vt. Okay, so that's this. So that's how we transform to get a distance from your, from my frame into your frame. And we'll go over another example, right? Let's say, but right, this essentially means that no frame is correct, right? There is no such thing, you know, this x prime is my frame, x is your frame, but there is no base frame, right? Because the base frame is on it's on a rotating surface of a planet, and the planet's going around a star, and the universe is expanding. So there's no way to say that there's a rest frame. We do say rest frame a lot, but we just mean on the spinning surface of the Earth, right? That this could be any frame to any other frame. Bob could be running the other way, and then so this v, right, is the velocity of the x frame relative to the x prime frame relative to x. So v is how fast I'm moving, right, relative to Bob. But if Bob starts moving left, then this v becomes, my velocity minus Bob's velocity relative to, the train station. So at this point, we have like VA, VB. We'd have VA minus VB is this, right? So there's no correct frame. So let's say I'm on a train. Again, I'm on trains a lot, and this train's moving at v, and I have a ball, right? And I throw the ball. Then the distance the ball travels in my frame is x prime. The distance it travels in your frame, so you're seeing it, this ball moves some x. The v, right, the velocity that I add to this ball, we call u, right? U prime. You see it with velocity u. Okay, well, we know that x dash equals x minus vt. There's this thing called an inverse Galilean, right? And that's the x, we just invert it, plus vt equals x. So this thing helps us get from this view into this view. It helps us find out what all of these quantities are equal to in this frame. This lets us go the other way around, right? Actually, sorry, this transform gets things from Bob's view into mine. This transform gets things from my view into Bob's. So for instance, we know, again, speed is distance over time. So speed times time is distance. So we can say that this is vt. We can say that v prime t, or sorry, u prime t plus vt equals ut. We cancel the t's, u prime plus v equals u. Well, we can say that if I throw this ball and you're looking through the window and my train's moving at not 300, it's moving at 100 meters a second, and you're moving at 0, like relative to me, if I just drop it, it moves at 0. I'm moving at like x is 0 for me. But for you, or let's say I throw it at 5. For you, you get this 100 of the v plus 5, and that gives you 105 in your frame. So you see me throw the ball, and for you it moves at 105. For me, it moves at 5. Right. Supremely obvious and boring, right? Like everyone knows this. It's just in your head. This makes sense. But you do need to calculate for this when you're in a game engine. So for instance, let's say you have a bad guy, an enemy, and they're shooting a rocket launcher at you, and they're an AI, and they shoot a rocket, and I'm here. We're playing Halo, right? And I'm running in a straight line over here. Or actually, let's just make it straight up. Then in the frame of this person, right, I'm here, the rocket is going to go straight at me. But in my frame, I see the rocket go like this because I'm moving forward, right? So to compensate, this AI is going to have to lead shot me and shoot in front of me, and then he can blow me up, right? So that's a simple example. Let's say this week I made this game with a bird. The bird has a bow, right? And the bow fires arrows. Okay. Now the bird can fall. Let's see the bird falls at 5 meters a second. Okay. And if you decide to shoot the arrow down, but your arrow only goes at 2 meters a second, right? Then because of this good old formula that u prime equals, wait, let's grab it again. U prime plus v equals u. In my frame, right, this is moving at 2, right? Sorry, I'm u prime. And my entire frame is moving at 5. Right, so it goes down 7 in the real world. But if I in general just set it in the world frame, when you set velocities, right, in Unity, if I do r dot velocity equals some value, right, then that velocity is in the world frame. It's not in my personal frame. So if I want this velocity to not mess up, if I just set this velocity to 2 every single time, regardless of how I'm moving, if I just always shoot it at 2, then if we imagine, okay, in the game frame, right? So in this case, our prime is the camera and the character. Let's say the camera's moving at the same speed as the character, and our x frame is just the world space. Okay? Then, if we look here, we have the velocity I'm setting to is -2 here. Well, in my u prime frame, it's going to be this it's 2, minus my velocity 5. So it's going to be -3. So since we set down as positive, it's going to be negative. So it's going to be 3 this way. So as I'm falling, relative to me, my arrow is going to go up because I'm falling faster than the arrow. So it's really important that when you fall, you add the arrow's velocity. You add your own velocity onto the arrow. Okay? So we can talk about let's talk about how you do it really quick. I'm probably going to give you a lesson on Quaternions, I've decided, because I think it's important. well, what you do is you instantiate your thing, right? So you have game object my arrow, right, equals instantiate. I hope you cache your objects, but for now we're not gonna. Instantiate arrow times, say you've got some bow point, right? Bow point dot position, right? And then you need a rotation, right? Your rotation, it's important to note, you have this function a_tan_2. You can put in your right sticks y or x here, or you can put in the relative position to the mouse and you. I'll talk about this in the next lecture. So let's just say you're using it with a controller. You can put in this and it will give you the angle from there, right? If this is the origin, it gives you this angle, right? It's always from the horizontal. A_tan_2 always works from the right horizontal, and it gives you the anti-clockwise rotation. And this is really important. A_tan_2 is a... the reason it's important is when you get projectiles in your game and you get asking artists to draw you assets, you try and get them to draw them facing right. It's going to make your life a lot easier, because then what you can do is you can do a Quaternion dot Euler angles. They don't like you using this function. It will be like, oh, this is a deprecated function. The reason is this one uses rads. Quaternion dot Euler uses degrees, which we don't want here. And Unity hates you using this, but I use it all the time. I've been using it for 10 years and they've still not got rid of it, so I'm sure it's fine. So otherwise you'd have to do, math dot rad to deg times whatever. So if you put in this a_tan_2 rs.y rs.x, right, you're going to get some matrix Q which rotates anything by this angle. So if we take this angle, this is vector 1, this is some vector and it's 1, 1, right? And we do Q times this vector. This Quaternion is just a rotation. It stores a rotation. So this thing's gonna, if this one was, 30 degrees or something, right? Then it's gonna rotate this by 30 degrees. If it was here, if you had a negative vector, it would rotate it to here. That's the really powerful thing about Quaternions. You can multiply them by normal vectors, not just each other. You can multiply them by vectors to rotate them. So if you have your character's rotation relative to this point, you could just transform everything by the Quaternion and it fixes everything. So for instance, when I set this thing's velocity, if I say my arrow dot get component rigid body 2D and set its velocity, I can say it's equal to the Quaternion, this Q, right, multiplied by some vector to 30, 0. That's my base speed, right? And that's the base speed rightwards. This Q will now rotate both my speed and my arrow to the correct angle. Okay? But then that's not enough. At the end, we then have to add on, right, the my velocity. Because otherwise, as we said, right, this thing, we need to add on my velocity at the end. It's not enough to just shoot it at the position. Now, I didn't do that in my game last weekend because I couldn't be bothered. But but if you go play that, you'll see that it feels wrong. But I just didn't want to do it because it was a game jam. So let's say, and because of this, you can do other things like this. Like the first jam game I ever made was called Rude Bear, and you're a bear and you're in a park. And I spawned all of these, the backgrounds. Well, they're actually as tall as the screen, right? I spawned all these squares with the background, and as you walked by, I would teleport these ones to the right to to make the level keep appearing, right? So the camera, right, the camera and the character both moved rightwards through the world. But then my fourth jam game, Rude Bear X, I did a similar thing, but all of the platforms came left at you, right? And the character only moves relative to the screen slightly, right? And the character's constantly running because it's in the V frame, it's not moving in this frame, so therefore it's moving in this frame, in the world space. So you can see that if you really want, you could make an entire game where the entire level always moves at you instead of you moving at the level. A good example of this, actually I don't know if this is true. No, it's probably not true. I don't know. Look up Super Monkey Ball. Super Monkey Ball, the whole level turns. You're not actually controlling the character. You're controlling the level, and the level is tilting. But it feels like you're controlling the character because it's the same thing. Or maybe it isn't, I can't tell. Because it's impossible to tell within the frame whether the world is rotating and they're just then shifting the background, or whether the character's moving. You can't tell. It's impossible to tell these things. Right? You'd have to open up the source code to see. I want to... Okay. We'll move on to, really quick, your assignment. Right. We'll talk about platforms. The biggest problem in game development for beginners. Okay. This is the biggest problem most people have when they're making a platformer game, at least. Right? It is the biggest problem in platformer game development. Let's say in real life, I'm on a bus. Right? We're all on a bus, and the bus is stopped, and we're just like chatting, and then suddenly, voom, the bus starts moving. Or the bus decelerates really quickly. Everyone on the bus goes, ah! You've all been on a bus, and people are, ah! They've been thrown around suddenly. Because the bus is just set off, and everyone's just been thrown back, except the clever person who's planted themselves down and is holding onto the thing. And even they swing, the thing swings back and they're wobbling and... Right. But then after a couple seconds, everything's fine. You use your friction and all the normal reaction forces of the seats, and all the drag stops being a problem because all the air in the back of the bus gets pushed forward by this air and this air, and eventually all the air in the bus is going forward, all the people in the bus going forward, and you all have this new inertia that's forward, right? But now imagine you strapped a chair to the top of a bus and you were sitting here instead. Then it would be very uncomfortable for you all the time, because you would feel as if a great wind is blowing in your face. Because this wind relative to you would be hitting you, right? So it is entirely normal that if something's moving very fast, if there's a skateboard rolling down the hill and you try and jump on it, right, you're going to fall off it. It's going to be moving too fast for you, and you're just going to go flying, right? Well, you're not actually going to go flying at all. You're going to fall over, but you're going to acquire a little bit of its velocity and then just topple and fall, okay? But in a video game, we want a completely different, nonsensical behavior, which is I fall on a platform and I gain its velocity, right? Moving platforms. Now, there are some ways in which moving platforms can be easy. If I have a platform and I have a little graphic over it that has like a skull face, right? And I want this to move with the platform, well, I can just make this a child of the platform and they'll have the same velocity. The problem begins when I add a rigid body to this. As soon as I have a rigid body on it, this isn't going to work anymore. Right, because these are two different objects that have their own motion. Okay, I can't just parent this to this. Now, if we're in one of these games where, you press right and it sets your velocity to 5, then okay, you can say, you can just add this velocity on, right? You can just say my new velocity is whatever my input velocity is plus the platform speed, because I only have three speeds: 0, 5, and -5. A lot of games do this, right? Right, but we were talking about the loveliness of force-based control and how you can have, you can move a little bit or you can move a lot and you add on a force. We can't just say, if this velocity is called the VP, the platform velocity, right? We can't just say our V is our current velocity plus the platform velocity, because this is an acceleration, right? We're accelerating, so every single frame, we'd be constantly accelerating, which is a problem, right? This isn't going to work. We can't. Okay, another thing we could do is we could just try, when we land on the platform, we can say, okay, so now my V is the V of the platform. Okay, fine. First of all, you're going to lose one frame here because you collide, right? And then it moves once, and then it starts setting it. So you will actually see yourself slip back in the platform frame, right? If we're looking in the platform frame, you'd see the ghost of you hitting it, and then you would move back one step, right? But ignoring that, that's actually not such a big deal, because, of course, in real life, when a bus moves, you would expect to jolt back a bit. So players don't really care about this, right? But you can't just do this, because remember, what forces are acting on you? You've got gravity, which isn't a problem, right? We've got no friction, but we do have a drag. And the drag is lerping you to 0. Right? It's always trying to push you to 0. So you have this force. You're like the man on top of the bus who's having wind blown in his face, and you're going to be blown off. So how can we reconcile this problem? How can we fix this? Well, we can simply take the drag function, which currently may look something like, remember, it's minus bv dt, right? So you have some v is v 1 minus bv dt. So you've got your initial velocity minus your bv dt velocity, right? That's the same as v times equals bv dt 1 minus bv. Yeah. Well, okay, for it. We've already done this before, right? Do you remember, like, v? I can say v times equals 0.9, right? And that's the same as v equals v times 0.9, which is the same as v equals v 1 minus 0.1. So in this case, right, this 0.9 is 1 minus bv dt, right? So we can do this every frame, and we'll get v is 0.9, then we'll get v is 0.81, then we'll get v is 0.729, right? So this is going to keep decreasing, and you'll see eventually the graph is going to look like this, and the drag is lerping our velocity to 0. This is a lerp, because it's going, it's going 10% of the way every frame, in this case. And all of them are some kind of lerp, a linear interpolation, right? So instead of lerping the velocity to 0, we should modify this formula so we're instead lerping the velocity with the same drag constant, right? We're still using bv dt, but instead of lerping to 0, we're instead going to lerp to the velocity of the platform. And if you can do that, then you fix the moving problems, the moving platform problems. Well, it's 2 steps, right? You land on your platform, and you inherit its velocity. Your velocity equals the VP immediately. Then you cache this VP, or you cache the object itself. So even if this accelerates, it's not a problem much. There's floating point error, but whatever. You cache this object's velocity, and then you can every frame say, okay, well, my drag is lerping to the object's velocity by the drag factor. Okay? Or, well, not or. And then what you can do is when you jump off it, you might want to retain that velocity for a bit. So, you know, when they're on a moving platform, you might want it that when they jump, they don't immediately lose all that velocity. Like, they still retain it. So when they're on this platform and jump and come down again, right, then they're still gonna be in the same place. So you could say that after, you know, it ramps off, or after like 1 second, then you lose, you know, you lose this relative velocity, and it clamps down to 0. Now we're going to be talking about lerps later. I would have liked to have taught you about lerps first, but this is the order of. I really need to teach you this stuff afterwards. After we've covered all of the basic stuff. Well, once we've covered waves, then we can start covering lerps, because we need to cover damping. But right now you could just use a lerp function in Unity. We'll talk about better ways of doing this and all the magic later on. But essentially, yeah. One more thing, you might be like, well, why can't we just disable drag? Why can't, when you're on a moving platform, why can't you disable drag? Why can't drag just be 0? Well, if drag is 0 and you got a really long moving platform and you start running, you're going to accelerate up to infinity, right? You're going to get ridiculously fast because you've got no drag that's slowing you down anymore. So it's not good enough to do that. The drag needs to push you towards the velocity of the platform. And that is your assignment. Now, I really wanted to talk about special relativity. But you know what? I'll do a lecture on that at the end. That'll be a bonus lecture at the very end, where I'll teach you some time and space craziness. Because we're going to get through so much of the course. If you looked at the spec, I've not been given a syllabus. I'm just writing as I go along. But the syllabus I was given to teach you, we're going to be done in like 3 lectures already, and that's like halfway through the course. So we're going to get into. You're going to get twice as much as you bargained for. You're not just going to get what they were taught last year. You're going to get basically double that. Hopefully, I'm not doing it a confusing way. But the thing is, when you learn traditional physics, they make you sit around being like, okay, now draw a force diagram. Now what's this velocity? Now what's this? In reality, when I'm in game development, how often do I sit and draw a force diagram? Absolutely never, right? I just go, okay, well, this needs a force on it, and then I add it with a line of code. So as long as I can teach you how to write a line of code that does gravity, then you don't need to think about, oh, well, what's the balancing of this force and this force and this force and this force, and how is it on paper? And if you really do, you can look up these things. I can point you to some problems if you think you're not understanding it and you want to solve it on paper. But I think paper is actually a bad way to teach this stuff when you're not even going to be using it on paper. And it's pretty simple in a game engine when the game engine does all the heavy lifting and the heavy maths for you. You just have to know just enough maths to write the formula in. You don't know how to. You don't need to know enough maths to propagate the formula in 50 steps or whatever. So I wanted to teach you special relativity, and I also wanted to teach you some shader stuff. And it's actually the case that I'm realizing now that we got 28 lectures. It's a lot of content I'm going to have to teach you. So I've always wanted to learn shaders and haven't known them. And I'm like, well, if I just learn shaders in the meantime in these weeks off, then maybe by the end of this course, I can teach you some cool physicsy shader stuff. I at least already in this lecture was going to teach you a little bit about shaders and how they relate to relativity, but we don't have time. So I'll just shove that onto the start of next lecture. It's only 1 slide. Right. So we're done now, right? Yeah. I will see you. Well, unless any questions. Oh damn! My camera stopped recording. Oh, it didn't hit the beep beep. That's just unfortunate. Right. Well, this lecture's gonna have half voiceless. Any questions?